Hi everyone, we're Soren, Adriana, and Juni, and in this presentation, we're going to introduce our project on adaptive DQN to enhance performance through test-time adaptation in the face of covariate shift. We're going to start with our research problem and some related work, then go over our method, results, discussion, including limitations and future work, and finish up with conclusion and our contribution. First, we're going to introduce the problem that we have identified. Real-world environments have a challenge called covariate shift, which is when the deployment environment is different from the training environment. For example, if we take an example of self-driving cars, we can imagine a scenario where we train our model on daytime images, but it can be deployed at nighttime, which changes the data distribution during deployment. This negatively affects the model performance. You can see how that needs to be addressed to make reinforcement learning more reliable in the real world, but we found that there is very little work dealing with covariate shift in RL specifically. Most of the work dealing with covariate shift is actually in supervised learning. As a background, we will introduce one of studies like that. They utilized an adaptive batch normalization layer. Usually, the statistic for batch normalization comes from the training batch in both training and testing phase, which makes the model performance poor when training data is even a little different from testing data. To mitigate this problem, this work makes the batch normalization statistic be abandoned in test time and instead uses the statistic from the testing batch during inference. With this, the model can adapt its prediction to testing data. We use this idea for our project. So this is the overview of our actual project. We use the Atari learning environment, but add covariate shift to the input images during test time. We confirmed that the traditional DQN performs poorly with the covariate shift added, so we set out to make AdaDQN, which is an algorithm that we hoped would perform well under various kinds of covariate shifts.
These are some examples from our Pac-Man games environment with covariate shift. We generate 9 standard types of covariate shift according to previous works in this domain. For each type of shift, we also generate 5 levels of severity from weak to strong as shown in the slide. This is the overview of our main experiment. Firstly, we normally train DQN with original Atari game environment. Once we get a well-trained model, we test it under our covariate shift environment to observe the degradation of DQN. Finally, without any requirement of retraining, we can simply plug our AdaDQN to the trained model and test it under our same shifted environment to observe the improvement from the original DQN. This is how our AdaDQN works in detail. We adopt the idea of adaptive BN layer we introduced in related work section. We integrate adaptive BN layers to our Q model, where it uses the statistic from the testing batch during inference. With this adaptive BN layer, we hope that Q model can adapt its prediction toward the current test batch and improve the performance of agent under covariate shift environment. This is detail of our experiment and evaluation. We use model architecture follows the previous work and evaluate the performance in these 4 Atari games, each trained with 3 million time steps. For the performance metrics, we average the episode return for 1000 episodes to see the performance of agent under a given environment. These are the results of our experiment. We found that our AdaDQN not only consistently outperforms the different level of covariate shift, but also maintains a robust performance in unshifted environment. The full results with different severity can be found in the main paper. We also perform a statistical analysis of the average episodic returns in phonic game. The results suggest that our improvement is actually statistically significant.
In discussion section, experimental results and statistic analysis underscores effectiveness of our method. One notable observation is stability of adaptive DQN's performance across increasing levels of severity. We believe that adaptive DQN has the potential to be a faster and reliable model for general reinforcement learning tasks.
To summarize our 3 main contributions, first, we implement the very first Atari game environment with covariate shift. Second, we demonstrate a significant drop in performance of DQN in covariate shift environment during deployment. And lastly, we propose AdaDQN, an effective algorithm that adapts the model to shifted data without retraining the model or requiring additional data apart from current test sample. Our proposed AdaDQN yields a higher average episodic reward compared to original DQN. This contribution can be leveraged in real-world settings, such as autonomous driving we introduced from the beginning.
This is our references. Thank you for listening.